from the previous slide, we have established that related rate is equivalent to having an equation that contains several derivatives. So we are going to use an example to illustrate on this idea. But before that, I would like to put this main idea in front of the next, at the top of this next slide. So we have this idea of related rates. Being mathematically equivalent to having an equation with many derivatives, more than one. Sometimes you can have 2 or 3 within that equations. So we are going to use this example number 1 to illustrate this idea to make you see how it's equivalent. So we have this situation created. So we have this air pump which pumps air into a balloon. Okay, so we have this setup and we want to study how the size of this balloon changes over time. Want to study how the size of this balloon changes over time. So in order to do that, we are going to introduce 2 variables into these problems. The first one is the radius of this balloon, and the other one is the volume of this balloon. So 2 variables. First one is the volume V, and the next one is the radius R. And once again, we want to study how this shape of the balloon changes over time, which means that as time passes, V is going to change and R is going to change. So in the end, we want to see the change of V with respect to time, and we want to see the change of R, the radius, with respect to time. With these 2 rates, we want to find the relationship between them. So in the end, we want to find equation containing them. Okay, but at the beginning, we don't have that kind of relationship to work on between dv by dt and dr by dt. So we are going to have to start somewhere else. So in order to do that, we are going to use something that we know from long time, probably in high school or something. So from high school, we know that the volume of a sphere is equal to 4/3 pi r cube. Okay, this doesn't look good, so let me erase this. Right, yeah, looks better. So we have this formula for the volume of the sphere available here. So we are going to start from here, which has physical meaning. In this case is the volume of a sphere, and we want to go from here to find the relationship between these 2 rates. In order to do that, it's not so simple. We are going to have to rely on a technique that we learned from last week, which is the implicit differentiation. So if you remember, to do that, we are supposed to take derivative of both sides with respect to time. Okay, so this stays the same, everything stays the same, 4/3 pi r cube. So here I take derivative of v with respect to time. In the end, I get the rate of v with respect to time equal to, here I have some constants. Constant doesn't matter in this case, so it comes to the front. So I have 4/3 in the front and pi in the front as well. Then I have this differentiation goes directly to r cubed. Okay. So r cubed, I need to apply the power rule. This has the power of 3, so 3 comes down and r stays the same and the power of r decreases by 1, so I have 2. But then again, I know that r depends on these two things, depends on t. So I can't stop this equation like this, so I have to apply differentiation to r as well. So that's why I have dr by dt at the end. Once again, this shows up because r depends on t. T affects r. You can't stop differentiating without having this dr by dt term coming out. So with this, we can clean up a little bit to make it look nicer. Cancels 3. So in the end, we have this dv by dt equal to 4 pi r squared, and we have dr by dt right here. So with this, in this equation, we can see that we have a relationship between dv by dt and dr by dt, two rates in one equation. So this equation is what we were looking for, is this the relationship between dv by dt and dr by dt, what we look for. So here we are looking at related rates, and we have the rates for the volume and the rate for r, and of course we have two first derivative, dv by dt and dr by dt. So here we start from the physical meaning of volume, and in the end we find the related rates, and we are going to make use of this later. So this is an example that shows how we construct this relationship between rates from physical meaning. So in order to make it easier for you to follow, I would like to move on to summarize what we just did over here to make it a guideline, like the keys for you to follow. So when it comes to related rates, the first thing I would like you to do is to construct an equation that relates all variables. Construct an equation that relates all variable. In the previous examples is this equation, the equation that relates v to r. So in this case, this is the first guideline to follow. And usually when it comes to this equation that relates all variables, it has physical meaning. Sometimes it's volume, sometimes it's area, sometimes it's just geometry. Could be volume, area, and geometry. Something that has its own formula, something that you have seen before. So once you have this equation set up, what you need to do is to apply implicit differentiation. Apply implicit differentiation Of course, and this has to be with respect to time. After we apply implicit differentiation, we are going to get the value of rates. Just like above, as you can see here, starting from this physical meaning, once we apply the implicit differentiations, we get these two rates from the process. So apply implicit differentiation, you get rate, and then maybe you need to rearrange equations if needed. Okay, so number 2 is done with the apply implicit differentiation, and then number 3, in the end you are going to have to solve for the unknown rate. Okay, so mostly the problems is going to give you one unknown rate, and the information for other rates should be given. So in the end, you just need to solve for the unknown, and then the problem is done.